Swayam Prabha. Digital India. Educated India.
Welcome back. So, today we are going to solve diffusion equation for another set of boundary conditions. It is called diffusion couple. A diffusion couple is formed when you have two blocks of different compositions which come into contact of each other at an elevated temperature. So, at the elevated temperature, the components diffuse from one block into the other and the interdiffusion process occurs. Now, we will talk about infinite diffusion couples, which means the thicknesses of the two blocks in the diffusion couple that we are going to consider are large enough, so that the diffusing species do not diffuse all the way to the other ends or all the way to the terminal ends of the two blocks. Okay. So, the problem is like this. We have two alloy blocks. The initial contact plane, that is denoted as x equal to 0, and the starting concentration of left side alloy, that is denoted by C minus C superscript negative sign, and the starting concentration of the right side terminal alloy is denoted as C plus. We will first consider binary diffusion couples, which means there are two components, and so the composition of each of the block can be specified by just one concentration variable. So, we have to solve the diffusion equation dou C by dou T equal to d time dou 2 C by dou x 2. Let us call this equation 1, and it has to be noted that we are making two assumptions here when we write this equation. The first one is that d is constant or independent of composition, and secondly, the molar volume is also assumed constant. And the initial condition is, since we are dealing with infinite diffusion couples, so the two terminal ends we denote as minus and plus infinity. So, we have on the left terminal is x equal to minus infinity, right terminal is at x equal to plus infinity. So, the initial condition is C at any position x at t equal to 0. Now, we have a step function here, right. The left terminal alloy initial concentration is C minus. So, for all x less than 0, C at x 0 equal to C minus, for minus infinity less than x less than 0, and in the right terminal alloy the concentration is C plus. So, for all x greater than 0, that is 0 less than x less than plus infinity, C at x 0 equal to C plus, and the boundary conditions are at x equal to minus infinity at any time t, the original concentration of the terminal alloy will remain. So, C at minus infinity t equal to C minus, and C at plus infinity at any time t is equal to C plus. So, we have to solve the equation 1 with respect to these initial and boundary conditions. So, we will derive the solution for this with two different approaches. First, we will use what we have been using so far, the Laplace transform approach. So, for Laplace transform, we start with taking Laplace transform on both sides of equation 1, which means we multiply by e to power minus k t and integrate from t equal to 0 to infinity on left hand side as well as right hand side. We take the Laplace transform, d is constant. So, we take d outside the integral. So, right hand side becomes d times integral 0 to infinity e to power minus k t dou to c by dou x 2 dt. Since e to power minus k t is independent of x, so we can take this term inside the partial derivative. If we solve the RHS, right hand side first. So, RHS is in d times integral 0 to infinity dou 2 by dou x 2 of e to power minus k t times c dt, and then we can change the order of differentiation and integral. We get d times dou 2 by dou x 2 of integral 0 to infinity e to power minus k t times c dt, and this integral is again familiar. It is nothing but the Laplace transform of c of x and t, which we denote as c bar, and the Laplace transform is independent of time. So, we can replace the partial derivative with ordinary derivative. So, this becomes d times d 2 c bar by dx 2. Now, let us solve the left hand side. LHS is integral 0 to infinity e to power minus k t dou c by dou t dt. Now, let us use integration by parts here. And we know the formula for integration by parts, integral a to b u dv is equal to u v from a to b minus integral a to b v du. So, if you look at this integral here, we can write u equal to e to power minus k t and dv equal to dou c by dou t times dt. So, du is minus k e to power minus k t, and the function v is nothing but c. So, we substitute here, we get c times e to power minus k t from 0 to infinity. These limits are for time t equal to 0 to t equal to infinity, minus k becomes plus. So, plus k we can take it outside the integral, k times integral 0 to infinity v du e to power minus k t times c dt. So, LHS is, you know, c at t equal to infinity will have a finite value, and e to power minus infinity is 0. We have 0 minus at t equal to 0, the exponential term e to power 0 is 1, and c at t equal to 0, let us call it as c naught. C naught is nothing but c at t equal to 0 plus this integral is the Laplace transform of c. So, k times c bar. So, if we equate LHS and RHS, we find k times C bar minus C naught equal to d times d2 C bar by dx2, or if we rearrange the term, d2 C bar by dx2 minus k by d C bar equal to minus C naught by d. So, we could convert using Laplace transform the partial differential equation in x and t to an ordinary differential equation. Now, this is a non-homogeneous ordinary differential equation, which is of the form y double prime plus a y prime plus b y equal to c. So, a, b, c here are constants. Obviously, a is 0 in this case, b is minus k by d, and c is minus c naught by d. Now, to solve a non-homogeneous equation or to obtain the general solution for a non-homogeneous equation, we need to first obtain the general solution for the corresponding homogeneous equation, which in this case here is d2 C bar by dx2 minus k by d C bar equal to 0, and one particular solution for the non-homogeneous equation, and the sum of the two will give us the general solution for this non-homogeneous equation. Okay. So, let us first consider the homogeneous part. Which is d2 C bar by dx2 minus k by d C bar equal to 0, and it has a general solution. We have seen last time when we solved for the semi infinite slab boundary conditions. The general solution for this is C bar is equal to p times exponential minus root k by dx plus q times exponential plus root k by dx. Now, we need to know the particular solution for this. If you look at the right hand side of this non-homogeneous equation, it is a constant minus C 0 by d, right. So, the RHS can be expressed in the form k times e to power gamma x, right. In this case, gamma is 0, and we can start with the particular solution of the type C bar. Let us call it the particular solution as C bar p of the type beta. So, we can assume the particular solution as C p bar is equal to beta times e to power gamma x, and gamma is 0 here. So, it is simply C p bar is equal to beta. So, if we substitute this value of C bar in the non-homogeneous solution, obviously the second derivative of a constant beta is 0. So, we will get 0 minus k by d times beta equal to minus C 0 by d. So, this gives the value of beta as C naught over k, and the sum of the general solution of homogeneous part and the particular solution of the non-homogeneous ODE is the general solution of the non-homogeneous ODE. So, the general solution of this equation, let us call this as 2, becomes C bar is equal to p exponential minus root k by dx plus q exponential plus root k by dx plus C naught over k. Now, this C naught is the initial condition, C at t equal to 0, and it has different values for different ranges of x, right, because initial concentration profile was a step function. Now, if we look at the form of the solution, and we know that the concentration field should be have at all values of x, including x equal to plus minus infinity, right. We can straight away say that for negative values of x, p should be 0, right, otherwise C bar will tend to infinity. Similarly, for positive values of x, q should be 0, and then C naught is also different for negative and positive x. So, we can write the solution as C bar for x less than 0, p is 0. So, we can write C bar is equal to q exponential root k by dx plus C naught for x less than 0 is C minus, this is for minus infinity less than x less than 0, and C bar is equal to p exponential minus root k by dx plus C naught for x greater than 0 is C plus over k for 0 less than x less than plus infinity. Now, we need to find the values of p and q. If we look at the initial concentration profile, and we know that d is constant, it is independent of composition here. So, obviously, at x equal to 0, the concentration should be constant, and it should be equal to the average of C minus and C plus at all times, right. The profile should be symmetric about x equal to 0, because d is constant, it is not varying with composition. So, that we can use here, because C at 0 at any time t is equal to C minus plus C plus divided by 2, and if we take the Laplace transform on both the side for this equation, at e to power minus k t times C at 0 t dt, the limit from 0 to infinity is equal to C minus plus C plus divided by 2, this is a constant, times integral 0 to infinity e to power minus k t dt. So, left hand side integral is nothing but the Laplace transform of C 0 t. So, let us denote it as C bar of 0 at x equal to 0, this is at x equal to 0, should be equal to C minus plus C plus by 2 times is a factor of minus 1 by k times e to power minus infinity will be 0 and e to power 0 will be 1. So, this will be minus C minus plus C plus divided by 2k. So, if we substitute for x, yeah, so this minus minus will be plus. So, this should be plus C minus plus C plus divided by 2k. So, for x less than 0 condition, if we substitute C bar at x equal to 0, that should be equal to q plus C minus divided by k, which should be equal to C plus C minus divided by 2k, and so q here is c plus by 2k plus c minus by 2k minus c minus by k should be equal to c plus minus c minus divided by 2k. And so c bar here becomes c plus minus c minus divided by 2 into 1 by k exponential x over root d times root k plus c minus times 1 over k. And for x greater than 0, we substitute for c bar at x equal to 0. This should be p exponential 0 is 1 plus c plus over k, and this should be equal to again c minus plus c plus divided by 2k. And so p here becomes c minus over 2k plus c plus over 2k minus c plus over k would be c minus minus c plus over 2k. And so c bar becomes c minus minus c plus by 2 times 1 by k. So exponential minus x over root d root k plus c plus over k. So we got the form of c bar, equation for c bar on both sides for x less than 0 as well as x greater than 0. If we take the Laplace transform, so let us first do it for x less than 0. If we take the inverse Laplace for x less than 0, we get back the function c is equal to c plus minus c minus by 2 is a constant into L inverse of 1 by k exponential x over root d times root k plus c minus is against constant L inverse of 1 over k. And the first function inside the inverse Laplace is familiar to us, right? We know that L inverse of 1 over k exponential minus a root k should be equal to 1 minus error function a over 2 root t. So if we try to bring our this in the familiar form, we know here a is equal to minus x over root d, right. So we can write c is equal to c plus minus c minus divided by 2 times 1 minus error function minus x over 2 root dt plus c minus. L inverse of 1 by k is 1. So if we rearrange the terms, we have c plus by 2 minus c minus by 2 plus c minus plus c minus minus c plus divided by 2. This is a negative sign. So error function minus x over 2 root dt, and we know error function of minus z is equal to minus error function z. So this we can write in the form C minus by 2 plus C plus by 2 minus C minus minus C plus by 2 error function x over 2 root dt, and if we subtract C plus from both the side and rearrange the term, we get the familiar form for the diffusion couple equation: C minus C plus over C minus minus C plus equal to 1/2 1 minus error function x over 2 root dt. Right, this we obtained for x less than 0. Now, for x greater than 0, we see C is equal to C minus minus C plus by 2 into L inverse of 1 by k exponential minus x by root d times root k plus C plus times L inverse of 1 by k, and if we compare with the familiar expression for L inverse, here A is equal to x over root d, and so we can write C is equal to C minus minus C plus divided by 2 times 1 minus error function x over 2 root dt plus C plus, and if we rearrange, we get C minus C plus divided by C minus minus C plus is equal to 1/2 1 minus error function x over 2 root dt. So, we get the same form for both x less than 0 as well as x greater than 0. So, we can write the solution in general as C at any x and t minus C plus divided by C minus minus C plus is equal to 1/2 1 minus x over 2 root dt, and this 1 minus error function is also called as complementary error function. It is denoted as ERFC. So, we can write it as 1/2 ERFC of x over 2 root dt. So, this is the solution that we obtained for a typical infinite diffusion couple. This we obtained by Laplace transform method. Now, we will derive the equation for concentration evolution in an infinite diffusion couple using another method, is called, that is by principle of superposition. So, let us draw the initial concentration profile. Let us denote the x coordinate now with y, will be clear soon why we are denoting it now by y. Y equal to 0 is the initial contact plane, and then we have two terminals at minus infinity and plus infinity. The initial concentration in the left terminal alloy is C minus, and the initial concentration in the right terminal alloy is C plus. We have already defined the initial and boundary conditions, and we have to solve the diffusion equation. Now, let us consider a small volume element of very small width dy, which is located at some coordinate y within the diffusion couple. Now, this small element can be considered as an instantaneous planar source for the diffusing component, right, and let us say its strength is d delta. Now, we have seen the solution for instantaneous planar source which is sandwiched between two infinite blocks, right. If you remember, we got concentration profile something like this. So, the instantaneous planar source was situated at this position 0, right, and the concentration at any position x. So, let us denote any position x here. So, this is y equal to x. If you want to evaluate the concentration at x because of the instantaneous planar source at y, we have found the equation for that, right, and that we know is C of x t is equal to d delta by 2 root pi dt exponential minus x square over 4 dt. Now, this whole diffusion couple can be thought of as composed of large number of such instantaneous planar sources, and from the initial concentration profile we know what would be their strength, right. On the left hand side, or for y less than 0, the strength will be concentration times the width C minus dy, and for right hand side the strength would be C plus dy, right. And if you want to find the total concentration at any position x, there will be the contribution from each of these source, each of this instantaneous planar source, and we can obtain the individual contribution by this solution for instantaneous planar source sandwiched between two infinite blocks, right. And if we sum the concentration field because of each of these instantaneous source, we will get the total concentration at this position x at any time t. Okay. So, C of x t would be nothing but integral minus infinity to plus infinity for all the sources. Now, from minus infinity to 0, we have a different strength, and 0 to plus infinity we have different strength. So, let us split this integral at 0. So, from minus infinity to 0, we know d delta for y less than 0 is C minus dy divided by 2 root pi dt exponential. Now, we need to know the distance between the source and the plane at which we want to find the concentration field. So, that will be x minus y. So, this will be minus x minus y squared divided by 4 dt. Similarly, integral 0 to infinity C plus dy over 2 root pi dt exponential minus x minus y square over 4 dt. So, let us take the constants out. So, C minus over 2 root pi dt integral minus infinity to 0 exponential minus x minus y squared divided by 4 dt dy plus C plus over 2 root pi dt integral 0 to infinity exponential minus x minus y squared over 4 dt dy. Now, if we substitute x minus y over 2 root dt equal to eta, then we can write dy is equal to minus 2 root dt d eta, and when y equal to minus infinity, eta should be equal to plus infinity. When y equal to 0, eta should be equal to x over 2 root dt, and when y equal to plus infinity, eta should be equal to minus infinity. So, if we substitute, c of x t becomes, now there is a factor of 2 root dt. If we substitute for dy, this factor of 2 root dt will get cancelled with this 2 root dt term here outside the integral, right, but it will take a form of error function. So, we will need 2 over root pi. So, let us denote this as c minus over 2 times 2 over root pi integral minus infinity to 0 exponential minus eta square d eta, and there is a negative sign there. So, we need to add this negative sign, minus c plus by 2 times 2 over root pi. Now, the integral limits have changed. When y is equal to minus infinity, eta is plus infinity, and when y equal to 0, eta is x over 2 root dt. C plus by 2 times 2 over root pi x over 2 root dt to minus infinity exponential minus eta square d eta. Right. So, this looks something similar to error function type of expression, right. We know error function z is equal to 2 over root pi integral 0 to z exponential minus eta square d eta. So, to bring to this form, let us split each of the integrals at 0. So, we can write c of x t is equal to minus c minus by 2 times 2 over root pi integral infinity to 0 exponential minus eta square d eta plus integral 0 to x over 2 root dt exponential minus eta square d eta minus c plus over 2 times 2 over root pi integral x over 2 root dt to 0 exponential minus eta square d eta plus integral 0 to minus infinity exponential minus eta square d eta. So, if you look at each of the integrals, they are error functions, right. So, if we write this minus c by 2 with the 2 by root pi factor, this is the integral infinity to 0 is negative integral 0 to infinity, right. So, this is negative error function infinity. Plus the second integral in the first bracket is error function of x over 2 root dt minus c plus by 2. Again, the first integral in the second bracket is negative error function of x over 2 root dt, and the second integral is the error function of minus infinity, is error function of minus infinity. We know error function infinity is 1 and error function minus infinity is minus 1. So, we can write this as c minus by 2 minus c minus by 2 error function x over 2 root dt negative negative plus c plus by 2 error function x over 2 root dt, and error function minus infinity is minus 1. So, this becomes plus c plus over 2. Again, if we subtract c plus from both sides and rearrange, we will get the solution c minus c plus over c minus minus c plus is equal to 1/2 1 minus error function x over 2 root dt. So, we derived this equation with the principle of superposition. So, basically each of the small element in this blocks of the diffusion couple can be assumed as an instantaneous planar source sandwiched between two infinite blocks, and by summing all their concentration field at any given x, we find the net concentration at that particular value of x. Okay. Now, let us quickly look at some of the features of this error function solution. So, this is a similar solution that we obtained for the carburizing problem, right. So, the similar properties will apply here. The solution is same except for this factor of 1/2. So, we will see that c plus, c minus and c plus, these are constants, and d is also constant. So, again we can say that c at any position x and t is a function of x over root t, and x over root t is also called as Boltzmann parameter lambda. What does this mean? Again, if we draw the concentration profiles, schematic concentration profiles at different times for an infinite diffusion couple, so these are the initial profiles, and at different times if we draw, this is T1, T2, T3. So, if we consider any particular composition, let us say C I here, and track its x position at different times. So, these are x1, x2, x3. What this relation tells me that x1 over root t1 is equal to x2 over root t2 is equal to x3 over root t3 is equal to the Boltzmann constant lambda of Ci. So, each composition plane in a diffusion couple moves parabolically with time. That is what we usually call it, okay, because x by root t is equal to constant. This is a parabolic relation that each of the composition plane follows in a diffusion couple, and this is an important property because this helps us in roughly estimating the penetration depths at different times, if we know the penetration depth at one time for a given composition plane. Okay. So, this diffusion couple is very important for in our class. We will use this diffusion couple concept quite frequently, because most of the experiments that we carry out to determine the interdiffusion and intrinsic diffusion coefficients are based on these infinite diffusion couples. Okay. So far we derived the expression for binary diffusion couple, but when it comes to multi-component diffusion couple, the problem becomes little more complicated, but we will also derive the equation for a multi-component diffusion couple. The concentration profiles of multi-component diffusion couples, we will look into it in the next class. Thank you.